All right. So in lecture 1 of strength of material 1, we want to look at simple stresses and strain. Our lecture outline is composed of 1, the introduction, 2, stress, strain, Hooke's law, and also some works examples as well. Let's look at Hooke's law. Hooke's law states that when a material is loaded within elastic limits, the stress is proportional to the strain produced by the stress. Okay. Anyone else to repeat what I just said? Okay, so this is what I'm talking about.
Yeah.
That is the Hooke's law says that when a material is loaded within elastic limits, stress is actually what? Directly proportional. The word is directly proportional to the strain produced by the stress. The reason why I say directly proportional is that we have inversely proportional and also directly proportional. If I say I'm proportional to you, it means that once I'm increasing, you are also what? If I say I'm directly proportional to you, it means that once I'm increasing, you are also what? Increasing. But if I say you are inversely proportional to me, it means that whilst I am increasing, you are decreasing. Do you understand the meaning of these two scenarios? So Hooke's was actually saying that when a material is loaded within the elastic limit, the stress, okay, yes, the stress is directly proportional to the strain produced by the stress. Okay, so he said that stress is directly proportional to the strain produced by the stress. So he said stress is directly, this is the symbol, directly proportional to the what? Strain produced by the stress. Okay, so these are them. Take note that this can be expressed in terms of symbols. Okay, and that is the symbol for our stress is written as this, and the symbol for the strain is also written as this. Okay, yes. So in terms of explaining this, if you know the formula, or if you can express it in terms of or if it can be expressed mathematically, then at the end of the day you are good to go, because when you see this, you know that this is your stress. If you see this, you know that this is your strain. But take note that for normal stresses, if I say normal stresses, that is it could be tension and what? Uh, compressive stresses. Okay. Yes. For normal stresses, uh, um, the our K that we are going to consider is going to be what? Elasticity. Okay. But before that, if we want to get rid of this proportional sign, what do you think we are going to do? We have to introduce a constant. Okay. That is, we say that Hooke's was saying that stress is directly proportional to the strain. Okay. But mathematically, if we want to get rid of this proportional sign over there, what are we supposed to do? You realize that we have to introduce a what? A constant. Okay. So in getting rid of this proportional sign, we have to introduce a constant. Then now we can bring our equal to. That is, if we are doing that, we are trying to derive a formula. We are trying to derive a formula. So at the end of the day, we are going to be getting our stress is equal to K, okay, multiplying the strain. Our stress is now going to be equal to K multiplying the strain. But take note that for normal stresses, our K is equal to E, okay? But our K is equal to what? E, okay? For normal stresses. So if we want to rewrite this again, how do you think this is going to look like? Now I've told you who case. I just told you who case. So how do you think this is now can now be written? This can now be written in the form of what? Our stress being equal to E. Okay, good. Multiplying our strain. So now tell me, if we want to get E, what do? We just have to divide both sides by strain. Then we are going to get our formula for our E. If we want stress, you realize that we can easily multiply our elasticity times our what? Strain, and we're also going to get strain. Okay. If we want our strain to, we just divide both sides by the E or the elasticity, and we're also going to get for our um, strain. But before that, I want us to make elasticity the subject first. So from wherever we started from to wherever we have gotten to, I want to pick some few questions before we continue. Anyone having any question to ask before we proceed? Is there anyone who has any question he or she wishes to ask before we proceed? All right, so I want to ask the class a question. What did I say about directly proportional and inversely proportional?
All right, this is Augustine here. Directly proportional means when the stress is increasing, the strain is also increasing. But inversely means when it's decreasing, it's also decreasing. Proportionality means equality. So the um, direct proportional is a plus and inverse is a minus. That's what I understand.
Can you explain inversely proportional well again? What is the meaning of inversely proportional? Can you give me a scenario to explain that? All right, you did.
That's to say,
Okay.
it is not um, moving accordingly or equally. That's inversely.
Very much. Thank you very much. You did very well, and I think I need to give you a round of applause. Okay. So I think that was what I said, and I always said that good students should have a pen and a paper beside them. That is when the lecturer is teaching. It's not all that he will be able to write on the board, so that when the lecturer make references to some important point, they can be able to jot them down. Smart students who are always able to do that, anytime the lecturer comes back to ask more questions, they are able to what? Make an account on that. You see, so he has done very well, and I'm very, very proud of him. That is exactly what I said. It is what? Stress is directly, the word is directly proportional to the strain, because as stress is increasing, strain is also increasing. You understand me? But when we say inversely proportional, it means that as stress is increasing, strain is decreasing. You understand me? So in writing the rule, please remember to use the right word. If you just say proportional, you need to be specific. What do you actually mean? Do you understand me? Are we all making sense here? All right. So on this one,
Yes.
that the laws of physics are the same for all observers in uniform motion relative to one another. So we said that stress is directly proportional to strain, and this is the same thing I've repeated over here. If you want to get rid of the directly proportional sign, that is, you are going to bring equal to and k according to the what? Rules of variation. I have a video on that. You can watch that on my YouTube channel, and you realize that you are going to be more history about variation. Okay. Yes. So stress is directly proportional to strain. To get rid of the directly proportional sign, we introduce an equal to sign. Okay. Anytime you introduce an equal to sign, it comes with a K. But for our normal stresses, K is equal to, okay. In that case, this is the formula that we came about with. So now if we want to find for E, E is our elasticity. If we want our E, we can say that E is equal to, we can say that our E is going to be equal to, let's say, stress divided by our strain. Someone just asked me, how did I come about with that? Okay, this is because when we're having stress is equal to what? Elasticity times the strain. You realize that if you want to make, let's say, E the subject, you have to divide both sides by this. Okay, you have to divide both sides by strain. And if this cancel this, finally you realize that you are going to be getting what? Your E being equal to stress over the hot. strain. Take note that your stress, there are so many ways of killing a cat. Do you understand me? So the formula to find for stress in this case, if you want to find for stress, what do you think the formula for stress is going to be? So now let's take this as our general rule. Okay, let's take this as our general rule, and this is our general rule that we are focusing on now. If you want to, let's say, find for stress from this, what do you think stress is going to be? You realize that your stress, okay, your stress into bracket this is going to be equal to what? Your elasticity, okay, times the what? Strain. Also, if you want strain, if you are looking for strain, if you want strain, what do you think is going to be the formula for strain? If you want strain, what do you think is going to be the formula for strain? Can anyone tell me the formula for strain? Let's say from here we want strain. What do you think is going to be the formula for strain? All right, Asari Bernard, please tell us, make us history.
Yeah, please. The strain will be stress over modular of elasticity.
You said strain is going to be what? Stress over what?
Stress over modular of elasticity. Yeah.
Is what you said. On any other contribution, though we are going to solve to verify that whether what he's saying is true or not. Okay. But before that, anyone with any different answer, your opinions are also welcome, please. Any other suggestion?
So I am used to the old formula that we learned.
No, let's
That
use this one.
okay, we should stick to this one, right?
We are using this one.
Okay.
I said this
All
is a
right.
general formula. Okay. So if you want to make,
Sure.
what do you think the formula is going to be? Derive that from this before we solve it together.
So this is John.
Thank you.
So the elasticity will be so that is elasticity will be equal to will be equated to that is
All right.
it,
All right. Thank you very much. You did very well. So let's say if you have this, let's say if this is your general rule, let's say E is equal to let's say stress over strain, and you want actually you are looking for strain. Then you realize that what you have to do is that you have to multiply, you have to do something we call cross multiply. I told that this guy over here, if you see A somewhere, A is not standing alone. No. This A actually divided by 1, it has 1 over here. It even have an exponent of 1, and it also has a subscript of 1. Okay, but in the scientific world, if you have eyes, you will see this. Okay, so this E over here, what do you think is under the E? It's 1. Okay, so that is happening over here. But in some cases you choose to write, in some cases you don't choose to write, because even any number divided by 1 is still the same number. So if you want your strain, that is, if you want to make this guy the subject, we have to just cross multiply. You see, we are going to do cross multiplication. And that is going to lead us to get a formula such as what? Our E is going to multiply, dot means multiplication. Okay, so our E is going to multiply the strain, which is now going to be equal to what? 1 times what? Your strain. So at the end of the day, what are we going to do? We divide both sides by E, and you realize that our formula is going to be what? Stress. Our strain is going to be equal to stress over elasticity. So I think our brother was right. Okay, our brother was right. So finally, let me quickly write this again before I divide so that we all don't lose the step. So this is what, this time, this is still going to give you this. And at the end of the day, if I divide here by E, and I divide here too by E, this is going to take care of this. So finally, we are going to be left with our strain. Our strain is equal to stress over E. Okay. So our brother was right. Whatever he said, he was right. Please learn how to make the change of subject. I'm actually doing all of this because if you're not good at change of subjects, you can even have the idea, but you realize that you may really struggle. Okay. So let's learn to do the change of subject. So let your main focus be on the general equation. The other ones are blessings, they are addition. Okay. Yes, they can also be explained in terms of quantities. Okay. So the stress is also actually force over area. Okay. So I'm still going to pick this general equation. You said at the end of the day, whatever I'm doing, I'm relating it to the general equation. Okay. That is why I'm saying that you don't need to struggle to chew the whole book. Okay. You can just understand one thing, and just that one thing that you have really understood, it can help you to come out with the rest naturally. What did Hooke say? Hooke is actually the man that I have used as our group profile picture. Yes, that is Robert Hooke. Okay. Yes. He made an experiment, and according to his experiment, he's a scientist. He found out that he was using springs, okay, and he found out that stress is directly proportional to strain. Out of that, he was able to come out with this formula, and that is what is even helping we engineers in real life today. Okay, so he says stress is directly proportional to strain, but for normal stresses, our K is equal to our E. Okay, so at the end of the day, we had this as our hot general rule, and from that, you realize that we can make E the subject. Okay, good. So let's proceed. Let's proceed. So you see that this is the formula for our, uh, so we can call this, so far we can call this equation 3. You see. Then the first one, what is equation 2? Our equation 2. So we can call this is our equation 1. Let me quickly relate. So this becomes our equation 1. And you see that this is our equation. How to put your main focus on equation 2, it will help you better. Okay. If you put your main focus on equation 2, it will help you better. At this point, I want to pick some few questions before we proceed. If there is no question, then let's continue to make history. All right. All right. So we are saying that our elasticity is equal to stress over strain. Okay. Uh, that is what we are saying from this equation 2. Okay. So let's repeat that. We are saying that this E is equal to, let's say, stress over strain. So let me write it fully this time. Stress over strain. But you realize that the stress can be expressed in terms of this, and then the strain can also be expressed in terms of this. Take note that this can also be expressed in terms of this. So the formula for the stress is equal to what? Force over area. You see? So the formula for stress is also equal to what? Force over area. Force over area. And the formula for the strain, change in length over what? Original length. Change in length over the original length. You can choose to express this too in terms of symbols. You can choose to express this also in terms of symbol. So let's say change in length. So this is change in length. Over the original length. Change in length over original length. You see? So these two, at the end of the day, if I want to just work with just symbols alone, still it can be expressed in terms of this. At the end of the day, please, let's learn how to do the change of subject. It is really going to help us very well. Okay, so we said that our E is equal to stress over strain. Also, this can be expressed in terms of this. So to avoid you writing in full, according to algebra, you can use some symbols, or even the symbol of force is what? P. In this case, the symbol for our force is going to be denoted as P. And then our A, we are going to use what? Area. Okay, good. For the change in length, how can it be also expressed? It can be expressed as what? You can use delta L. Delta L over what? L itself. When you see L somewhere, it means that original L. Okay. Yes, it means the original L. Take note that these two, if you don't want to write it this way, you can also still proceed to write it in this form. So you can also say, okay, let me come and write that downward. So we can also say that now we can say that our E is equal to P over A, or force over area, divided by change in length over original length. You see, just E alone, I'm expressing it in so many ways. Do you understand? And it all starts from the basics. If you really understand what you are doing, you realize that naturally it's going to flow. You understand me? So this is also the meaning of all of this. Our elasticity is equal to what? Stress over strain. But we said that the stress can also be expressed as what? Force over area, and the strain can also be expressed as change in length over what? Original length, and that is what we are using now. So you see, instead of me writing it this way, that is how, instead of me writing it this way, I can choose to write it this way too. You see, if I want to get rid of the division sign, what do you think I'm going to do? I have to reciprocate the other one. Okay, I have to reciprocate the other one. Okay, good. So finally, you realize that our E is going to be equal to what? P over A, or force over area. Force over area times original length over what?
Change in length.
So finally, what have you discovered? You realize that instead of rewriting it this plenty way, we can just choose to write it in a simple way. So finally, I can just write this as this, and then we start solving some questions. I think we are good to go. So finally, I can choose to write my E equal to, let's P L over. So if you see me putting dots over here, it means multiple. Okay. So PL over what? Area times change in length. Area times change in length. Please, any questions, any contribution before we begin? Any question, any question, any question, any contribution before we begin?
It looks so the contribution is that it looks way simpler this way than I don't know. That's what I think though.
Thank you, thank you, thank you. Okay, so I want to add one last more thing for recording purposes before we proceed. Okay. So now let's talk about the units. Now we've spoken about all of these quantities. Okay, we've spoken. They are quantities. Some of them are base quantities. Some of them are derived quantities. You see from whatever we've learned previously. So applying all of some of those things that we learned, now we want to write their units. You see that we learned that they have symbols. They also have units too. So let's focus on this one. Just this one alone, we can derive everybody. So what is the unit of, what do I'm coming? Let's write that over here. So let's write all of them. This is our E. E is equal to Now we come and write P. But before that, let's write over here unit of quantities. Unit of quantities. Units of the quantity. All right. So let's proceed. So the first one, we can see E. Also, I can see P. I can also see L. And the P is force. Okay. I can also see A. As we said, the A is our area. And then I can also see a change in length. Change in length. Take note. Please, everybody, I want you to jot something down now. Change in length I'm talking about here in some cases can be called elongation. In some cases, it can also be called extension. Okay, so put some of these things down. Change in length has various names. It keeps being dynamic. Okay, I can ask you to calculate the total extension. It also means total change in length. Do you understand me? I can also ask you to calculate the total displacement. Do you understand me? So you should be able to take some of or jot some of these important points down to make life easier. So the units, let's quickly write the units. We said that look at something.
Hello, sir, please, can you repeat yourself again concerning the change in length?
Change in length can also be known as extension. Change in length can also be known as elongation. Change in length can also be known as displacement. So you should take note of some of these important points so that if you meet it somewhere, you don't get confused. You know that it is this guy. He is the one who keeps changing that way. All right. All right. So let's proceed. So the E, we said that the E is equal to what? The E is our elasticity.
Elasticity, yeah.
The E is our elasticity. It's like I think I left some other quantities, but before even we talk about the E, I want to do something. That is, let me put strain over here. Let me put stress over here. Let me put strain over here. Okay. Then let's do it this way. So we say that this half hot, the strain is actually change in length over original length. You see, so if we are saying strain is equal to change in length over what original length, at the end of the day, this guy is measured in meters. This guy also measured in what meters. So if they cancel out, you say that this guy has what no unit. So it has no unit. Strain has no unit. Let's talk about the other people. Stress. We said stress is equal to force over area. You see, and force is measured in what? Force is measured in Newton. Stress is equal to force over area. Force over area. So area is measured in what? Meter squared, and also the area is measured in meter squared, and force is measured in what? Newton.
Newton.
But I told you that we are engineers, and
Newton meter square.
we are engineers, and because of we are working with rods, most of our calculations are in what? Millimeters. Okay. So in that case, we are not going to use meters, we are going to use what? Millimeters. Our areas are going to be calculated in millimeters. That is why I taught you the convention. So how do you think the unit is going to be in this case? The unit is just going to be what? Newton per what? Millimeter.
Millimeter square.
Second unit. Yeah.
Okay. I already told you about about P, and P is what? The unit of P is what? It's Newton.
Newton.
The unit of L is meters. The unit of area
Newton.
is the unit of area.
Millimeter square.
It is meter squared. But because of our calculations, we are in most cases we are going to be expressing it in what? Millimeters. You see that the length can also be expressed in meters or millimeters, and the area too in most cases we're going to be expressing it in what? Millimeter squared. See what we are talking about here. Uh-huh. What about the change in length? Change in length also have a unit of what? Millimeters. Okay.
Because
You meet it in a question somewhere and they write meters. Sometimes it can be for moments. You realize that moment is equal to force and perpendicular distance. In some cases, it may be m and you have to convert it into the other. In some cases, you have to maintain it that way. Okay. So the question is not asking you to calculate for it in meters. It may be asking you to calculate it in what? Millimeters. And the E, our elasticity. Now our elasticity, what are we going to say about elasticity? I already told you that the stress, we say elasticity is equal to, we said that elasticity is equal to stress over strain. You see whatever we were saying. So now we know that the stress is equal to what? Newton,
Newton per meter square. Square, millimeter square.
Newton per millimeter squared. And we said that what? The strain has no unit. So you realize that
No unit.
at the end of the day, elasticity is only going to absorb the unit of what? Stress.
Stress.
It's like Newton per millimeter. Okay. Man. But for the area there, I'll advise you that always calculate for your area in what? Millimeter squared. Yes. Always calculate area in millimeter squared. Okay. Can we proceed? Please, can we proceed?
yes.
So let's quickly take some questions. But before that, is anyone having any question? Any question? Any question? Any contribution? Anyone wishes to add? All right. So let me quickly put um a question and let's begin from there. So this is my most example. Okay. So we say this is our problem one on one. One is we are in lecture one and point one, example one of uh, one. Good. The problem we have to solve. First of all, I want someone to read the question for me and then we take it from there.
Okay, I'll read.
Okay.
A rod 150 centimeter long and of diameter 2.0 centimeter is subjected to an axial pull of 20 kilonewtons. If the modulus of elasticity of the material of the rod is 2 times 10 raised to the power 5 newtons per millimeter squared, determine one, stress, A, stress, B, strain, and C, elongation of the rod.
Okay. Thank you very much. Thank you very much.
So elongation change in length.
Any other person to read a question for us? Any other person to read a question for us before we proceed? Any other person?
Okay.
Okay.
A rod of 150 centimeters long and of a diameter 2.0 centimeters is subjected to an axial pull of 20 kilonewton. If the modulus of elasticity of the material of the rod is 2 times 10 raised to the power 5 Newton per millimeter square, determine A, the stress, B, strain, and elongation of the rod.
Okay. Very much. Another person to read the question for us last time before we. Hello.
Yeah, please, I read. A rod 150 centimeter long of diameter 2.0 centimeter is subjected to an axial pull of 20 Newton. If the if if the modulus of elasticity of the material of the rod is 2 times 10 raised to the power 5 Newton per millimeter square.
All right. All right. Thank you. So the question says that a rod 150 centimeter long, that means that is the full length of the rod, okay, and of diameter 2.0 centimeters is subjected to an axial pull of 20 kilonewton. I told you that we are engineers and all our calculations must be done in millimeters. So the length, which is 150 centimeters,